Flock is not here, but he had a good question that I could answer anyway. He was asking how to prove that the product of two connected spaces is connected.
I think I answered that for me.
Did you do that together?
We found proof.
Because I saw the notes in 206 on the board.
Oh, yeah.
Somebody did it. It's surprising. I mean, anyway, the path connected analog of that statement is totally trivial to prove, but the connected one. Okay. So we start with topological manifolds. And then refine to smooth manifolds. So the whole idea of a manifold is that it's a topological space that locally looks like a Rn, right? So we need to define first what that means. And definition, this is called a locally Euclidean space. So X topological space is locally Euclidean if every every point in it has an open neighborhood U sub x that is homeomorphic to Rn, or equivalently homeomorphic to a ball in Rn, let's say, but that's all the same. Okay. Next definition we've already seen before. A second countable space is one that has a countable basis of topology. We know that. So Rn, for instance, is second countable. And finally, we'll define what a paracompact space is in stages. So first of all, a collection of subsets of some space X is called locally finite if every X in X has a neighborhood, an open neighborhood U sub X, such that U sub X intersected with a alpha is non-empty only for finitely many alphas. So it's just a collection of subsets like that, such that every point in my space is roughly speaking contained only in a finite number of these sets. If these sets are all open, then this is literally the same as X being an element of only finitely many of them, because then the existence of these neighborhoods is follows by the definition of openness. Okay, is that clear? Number two, given, so let's say U alphas is an open cover of X, meaning that U alphas are all open, and the union of all of these guys is all of X. Then a collection V alpha, V, let's say beta, is a refinement of the U alpha cover. Refinement if every for every beta there exists an alpha such that V beta is in U alpha. So it's basically an open cover that consists of smaller sets, right? These would be betas. All right. And finally, X is called paracompact if any open cover has a locally finite refinement. I mean, this also has to be an open cover, right? Didn't mention that. But, so basically, you should always be able to remove the extra open sets from your cover, such that in the end, every point of the space is contained only infinitely many of them. Okay. And now we can define manifolds. Topological manifold is a second countable Hausdorff locally Euclidean space. So remember, Hausdorff is the property that for any 2 points, we can draw two open neighborhoods around both of them that separate, that don't overlap. Right? So that's Hausdorff. That's it. All right. And a proposition that you can prove is that all topological manifolds are in fact paracompact and locally compact. So locally compact is a lot of these local topological properties, and basically all of them are defined in a way, in the same way you take this property and you restrict it to a sufficiently small neighborhood of every point. So this means that every point X has an open neighborhood that can be embedded into a compact subset. Anyway, I'm not going to prove this, but it's in Lee. So actually, for the next few lectures, we're pretty much following Lee, intro to smooth manifolds. I have the references to specific theorems in the notes. Okay. He also has a book on topological manifolds that's separate, but we don't really need that. Okay. So the definition of manifolds that you usually see whenever spoken by a physicist, let's say, or like in applications, is another one using charts. So we can see the connection now. So let's define a chart. So let's say X is an n-dimensional topological manifold. N-dimensional means that the n over there in the definition of locally Euclidean is this n. Well, I guess strictly speaking, from this definition, it follows that a thing that consists of like a three-dimensional ball and then a two-dimensional disk separately disjointly is also a manifold, right? So on different connected components, you can have different dimensions. In practice, yeah, I mean that should be easy exercise. Because a two-dimensional ball is not homeomorphic to a three-dimensional ball. So anyway, a chart on X is a pair consisting of an open set and a map. So U open, so I'm gonna write it like that, an open set, and phi is a map from U into Rn. That's continuous and homeo to its image, right? So if I define phi of U as U hat, this is a subset in Rn, then this has to be a homeomorphism. Okay. Right. So we have our manifold, we have some open set, and we send this to Rn. What's that? No restrictions. I mean, obviously it has to be an open set because this is a homeomorphism, but that's it. Yeah.
What is the meaning for that notation between U and X? So
this means open subset. What's that? I'm just saying this is just equality, but this has to be homeomorphism onto its image, right? So between U and U hat, phi is a homeomorphism. There's two kinds of restrictions of maps, right? You can restrict the domain, like you have f of x equals x, right? You can view it as a map from R to R, and then you can restrict it to, let's say, R plus, and this will be a map from R plus to R, right? But then you realize it only takes values in positive numbers only. So you can also restrict it, restrict the codomain, and then reduce the target space, right? That's what I'm saying. If you restrict the codomain of phi to only its image, then it has to be a homeomorphism with the subspace topology on here. Okay. And also, if this U hat turns out to be a ball in this Rn, we call this chart a coordinate ball. Okay. And the values of phi are called coordinates of points on our manifold. That's it. Okay. So, of course, by definition of local Euclideanness, there exists a chart around every point, right? Because there exists a map that homeomorphically maps a neighborhood of every point to some open set in Rn. You can just take that map to be the chart. So there's always charts. And here's a big theorem that states some general topological properties of topological manifolds. First of all, so let's say you have a topological manifold. First of all, there exists a countable basis consisting of coordinate balls. And it also can be made locally finite. And every ball or every open set in this cover, in this basis, can be made pre-compact, meaning that U bar is compact. So its closure can be made compact. Compact is, for us, is basically an analog of small, right? Because in Rn, compact is the same as bounded and closed. On the general manifold, it's not immediately clear what bounded means. So that's just replaced by the general notion of compactness. So that's number one. This is basically saying that you can construct what's called an atlas. Consists of a bunch of charts that cover the whole manifold. That is like sufficiently nice, right? All charts map to balls, and it's locally finite, so every point is described only by a finite number of different charts and stuff like that. Okay, then local compactness. I already stated this before, but yeah, every topological manifold is locally compact. Locally path connected. So this means that every point has a open neighborhood which is path connected, and that's totally because Rn is path connected, right? It has at most countably many connected components. Each of them is open, of course, and a topological manifold of it. That also should be a totally obvious statement. At most countably many, because we need to have a countable basis. So if there's a countable basis, there's definitely at most countably many components. Yeah.
Ordinarily, a lot of textbooks define, instead of second countability, require paracompactness. If it was like, if we only require paracompactness, would like point 1 and 4 of the theorems still hold? Are they consequences of second countability, or? I can add to that question. Could we swap second countability and paracompactness and make an equivalent definition?
Usually that's done, but I don't think it's not an equivalent definition.
Second countability is definitely more a stronger definition.
Yeah.
Will the existence of a countable basis are like
Mm. Maybe not. I'm not totally sure. Yeah. Because second countability is explicitly used in the proof of these things. So,
could be that open cover itself.
yeah. And then the final thing here is pi 1 of x is at most So the fundamental group is at most countable, which is reassuring, I guess, because as we saw, fundamental groups grow very quickly with very simple operations on spaces. Yeah.
What is the meaning about most countable?
At most countable, like it has at most countably many elements, as I said.
Finite or countable, it can't be uncountably large.
Oh, okay, yeah.
I mean, the cardinality of the set, just the number of elements in it. So I will actually, so pretty much the only non-trivial statements here are number 1 and number 5, and I will skip their proofs. Where? I don't think so. And yeah. Okay, so I have a short proof of this in the notes, and then nothing about that. So lemma. For topological manifolds, locally, sorry, not for topological manifolds, in general topology, locally path connected is the same as path connected, and connected. Path connected plus connected is the same as path connected. And of course, every manifold is already locally path connected by definition, almost. So it's only enough to note that a manifold is connected to be sure that it's also path connected. So the proof of this is, again, using the trick that we know for how to prove that the set is open. So let's see how this works. First of all, this direction is obvious. So we're just proving that direction. So let's fix some point in X, and let's define a set C of all Q's that are connected to P by a path. Right, so P Q. The set of all such Q's is C. And we want to prove that C is all of the whole manifold, right? Given that it's connected. So to prove that, it's enough, because we already know that the manifold is connected, it's enough to prove that this C is both open and closed, right? Because remember, a space is connected if and only if the only clopen sets in it are the empty set and the whole set. And this is already not empty because it contains at least P itself. So we need to prove that C is open and closed. So let's prove that. So C is open. Why is C open? Why? Right, so local path connectedness, right? For every point inside C, there's a neighborhood around it that's path connected. And then all of the points in that neighborhood also have to be in C because they will be path connected by transitivity to P itself, right? So it's open because of local path connectedness. And now we need to prove that it's closed. So let's see. Okay, so how do you prove that a set is closed? So we need to prove that C is the same as C bar, right? What's a useful definition of C bar? The closure. Hmm?
How can you say that for any point in the complement there exists an open neighborhood at that point? And it's also in the complement. Because if you were path connected to a point in that open neighborhood,
Yeah.
then you get a contradiction.
Yeah, sure. Yeah, that works. Or from the point of view of closure, so a point is in closure if and only if every open neighborhood of it overlaps with C, right? But then that point has a path connected neighborhood which has to overlap with C. Therefore, that whole neighborhood will be contained in C. Therefore, that point itself is actually contained in C, right? So if every point in the closure is contained in C, then C equals C closure. So, yep. So from all this, C has to be X by connectedness, and therefore X is path connected because C obviously is okay. Yeah, so for manifold connectedness is the same as path connectedness. As a corollary of this. And in particular, all connected components of manifolds are path connected. All right, so let's do some examples. Manifolds, any open set in Rn is a manifold, right? Why? Yeah, because it's homeomorphic to itself. Okay, then let's say the sphere. Why is that a manifold?
I mean, that is just, well, never mind. I mean, it's the boundary of an open.
So yeah, so we can look at the sphere, right, embed it into our Rn, and like if my point is over here, let's say, I will just draw a circle and then project it onto onto this coordinate plane, right, and that will be my chart onto R2. If my point is over here, I will just rotate the coordinate system and project it onto something else, right? So I can always find a local chart, which will be a homeomorphism. No, all we need is to find local charts around every point. That's it. There's no other requirement, right?
One way of doing that is just consider hemispheres across every coordinate plane that you can. And just project those hemispheres down to the coordinate plane. Those are form a contour chart that covers the entire screen.
Okay. Number 3, the torus, right, which is the circle to some Cartesian power n, is manifold because, well, there's even a global, well, almost a global chart on it, given by m angular coordinates on the circle. First.
The angular coordinate isn't really a chart. I mean, so it doesn't completely cover.
No, I know. That's why I said almost minus some lines. The figure 8, right, in R2, with the subspace topology in R2, is that a manifold? Why not? What about it?
Isn't that not even Hausdorff? Right? Like, if you get to a certain point,
No, it's Hausdorff.
you can always pick very small intervals.
You can separate points on it, that's fine. But yeah, you need to show that this point doesn't have a neighborhood that's isomorphic to an interval on the real line, which we've discussed before, right? If any neighborhood of this thing looks like this, like a cross, it's homeomorphic to a cross. But a cross, if I exclude the center point, consists of 4 disjoint open intervals, whereas on the real line, any interval, if I exclude this point, I get 2 intervals, not 4, right? So connectedness is the topological invariant that separates this from a manifold. Okay. What's that? What does that mean? Oh, you mean it doesn't actually overlap? Like in 3 dimensions. Like in 3 dimensions, separate them. Then it's a circle, right? Yeah. Okay. So matrices, let's say of size n with real elements, that's also a manifold, right? Why is that a manifold? Yeah. Say like that. What about GL invertible matrices? Do you know any topological properties of GL as a subset, let's say, of Rn squared? If I perturb an invertible matrix, can I get a non-invertible matrix? Right, so that means that the set is open, right? Any sufficiently small perturbation leaves me in the same set. Every point of it has an open neighborhood around it. Therefore, this is an open subset of Rn squared, right?
Also, as you said, the determinant is a continuous map from GL and R squared to R. So the set of invertible matrices is the inverse image of R minus 0 of the determinant. So R minus 0 is an open set, so its inverse image has to be an open set as well as GL and R is open.
You just choose a particular matrix and it has some non-zero determinant, and then you can find the ball where it determine that by that one.
Yeah. So this is a manifold, you know, SL, SU, whatever, UN. These are all also manifolds, although that becomes less obvious, but basically you can construct charts on them and stuff like that. Yeah, so these are also algebraic groups, right? Because they are defined as solutions of some algebraic equations, like U dagger U equals 1, right? That's just a system of algebraic equations on real numbers, which, you know, the set of solutions of a system like that is not always a manifold. So it's more subtle why those are actually manifolds. Yeah, there are algebraic varieties in general. Like the figure 8 is an algebraic variety. All right, so that's it for topological manifolds. Move on to smooth manifolds. What are you laughing at? All right, definition. So now that we have a bunch of charts, if we can cover the whole manifold with those charts, that's called an atlas, right? So an atlas, so let's say X is topological manifold. An atlas is is a collection of charts, U alpha, phi alpha, such that U alphas form an open cover of X, period. um, and I'll also use the notation that U with two indices is going to be the intersection of these guys whenever it's not empty. Alpha, beta, gamma is going to be etc. Right? That, I mean, that's a subtlety that never mattered. Okay, so what does it mean to have a smooth manifold? It means to have a smooth atlas on it. So let's call this curly A. An atlas on X is of class CK, C infinity, C omega. This is called analytic, called smooth. It's called K differentiable. If for any alpha and beta and two charts corresponding to alpha and beta, the transition function that is defined as phi beta circ phi alpha inverse that maps from phi alpha of U alpha beta to phi beta U alpha beta are of class CK or C infinity or C omega. Okay, let me draw a picture for this. So we have our manifold. We have, let's say, two charts, and we have phi alpha mapping to something, phi beta mapping to something, and then we have this overlap, which maps to some part of this, some parts of this here, right? Then between these two parts, I can have this phi beta alpha. And now this is a map between two open subsets of Rn, right? So we know what it means for it to be smooth because we can differentiate on Rn or K differentiable, etc. So analytic means that it has a Taylor series that converges in with some non-zero radius of convergence at every point. So all of these examples are actually analytic. With those atlases that we constructed. Okay, so these are called transition functions. Any questions about this definition? Right. So on the topological manifold, these things are automatically continuous. Just because these are already homeomorphisms, we can invert them, combine them into continuous maps, right? But if they're actually better, but because they're actually maps between subsets of Rn, it's natural to ask like whether they're actually better than just continuous. Maybe they're differentiable. And if yes, then it's actually a smooth manifold, right? All right. So there's an equivalence relation on atlases because obviously there's many different ways to pick an atlas. And two atlases are called equivalent if A1 union with A2 is still an atlas of the same class, right? So if I have two different atlases, I will add some more charts by doing this union. I will add some more charts on top of these. If they're still compatible with the old charts in the sense that all the transition functions are still smooth, then the atlases are called equivalent. Right. And a CK, C infinity, or C omega structure on X on a topological manifold X is an equivalence class of CK infinity omega atlases. So equivalence class of atlases. So differentiable, smooth, or analytic structure. We're only interested pretty much in the smooth manifolds. So that's how you define. So a smooth manifold is just a topological manifold with a smooth structure on it, meaning an equivalence class of smooth atlases.
Isn't there some result which states that CK manifolds are automatically smooth?
Yeah. Was there a question?
Yeah, so I mentioned there, yeah. So is there a way to define maximal atlas specifically to cover this?
Yeah, yeah. Mm-hmm. I mean, the union of all atlases in the equivalence class is called the maximal atlas. Not a super useful notion, but yeah. Okay, so let's do some examples. I will transition now from using X's for manifolds to M's. So example. Let's say our manifold is R, and let's take a function which maps from R to R, defined by x cubed. And let's take this to be a chart, right? So R comma psi is a smooth atlas on M. It's smooth because there's no transition functions, right? So all of the transition functions are automatically smooth. All we need is for this psi to be a homeomorphism, which it is, because it's inverse x to the 1/3 is still a continuous map, right? This is actually a smooth atlas, and it defines some smooth structure on R. So let's call this a something tilde, right? And A will be R with the identity map, which is the standard. So this is a standard structure on R, smooth structure. So I claim that A is not equivalent to A tilde. Why is that? Yeah, one of the transition functions will be cube root, which is not smooth. So they're not compatible with each other. So this is a proof that you can have many different, in fact, usually infinitely many different smooth structures on the same manifold, non-equivalent smooth structures, right? Which is pretty interesting. So for instance, instead of x cubed, I could have used any function that's like a broken line, you know, it has a discontinuous derivative somewhere, stuff like that. Those are all different smooth structures. Mm-hmm. Okay. Another example, any real or complex vector space is a smooth manifold automatically because it's isomorphic to some Rn. I mean, homeomorphic. So we can transplant any of these, let's say the standard smooth structure, onto there. Spaces of matrices, classical groups, you know, spheres, GL, SL, they're all smooth manifolds. With the standard structures basically induced from as submanifolds of Rn. We'll discuss what a submanifold is later, but you can induce an atlas that way. Yeah, so an interesting note is that not every topological manifold actually supports a smooth structure. Even though like examples are pretty difficult to construct. And then, so not every topological manifold has a C infinity structure. Then every C1 manifold has a C1 compatible C infinity structure. So basically, you can improve every once differentiable atlas to a smooth atlas in such a way that the transition functions between the two atlases are once differentiable. So as good as it can be, right? So this essentially means that all differentiable manifolds pretty much can be automatically assumed to be smooth, which is why even in mathematical literature you will rarely read anything about those manifolds in between topological and smooth. Right? In dimension 1, 2, 3, all topological manifolds have a unique in this up to Diffeomorphism, which we'll discuss in a bit what that means, unique smooth structure. we'll get to that in a sec. So dimensions 1, 2, and 3 are kind of special, but in all higher dimensions, there are compact topological manifolds which don't have any smooth structures. And number 5, all V groups are actually analytic, which essentially follows from the proof of the convergence of Baker-Campbell-Hausdorff series. Okay. But if you don't know what that means, then don't worry about that. Okay, so to understand what diffeomorphisms are, we need to define smooth maps, right? So let's say M and N are smooth manifolds. A function f from N to N is smooth. What do you think? How? Hmm? What does that mean? Okay, what does it mean to be smooth at that point?
So we can associate with that the coordinate trace containing the 2 points we're looking at and talk about smooth maps.
What's the formula? So which map needs to be smooth? Okay, so if all what's called local representatives of f, which are defined as f alpha beta, is going to be psi beta circ f circ phi alpha inverse. I guess let's be consistent. Which maps from u alpha hat to v beta hat are smooth. Okay. So this is basically, for any chart phi alpha on u alpha in M to u alpha hat in Rn, and then Rm, let's say, and then psi beta v beta is going to be a subset in N, map into v beta hat subset in Rn. So I just take some arbitrary local coordinates on M and on N. If I convert the points on M to their coordinates, I take in coordinates, map them back to M, apply my map, and then convert the result to coordinates on N. This whole thing. Does anyone actually want that? Oh God. that. Okay. It's a commuting square, you guys. But yeah. Yeah. Analytic means that there's a Taylor series at every point that converges in some non-zero radius of convergence, right? Not every smooth function satisfies that. Infinitely differentiable. Yeah, and it has all derivatives of any order, right? Yeah, CK is only k derivatives, right? C infinity is any number of derivatives. Yeah. Yeah. Mm-hmm. No, there's no intersections. Its domain is the image of this chart, right? And then, they're separate spaces, right? Yeah. Every chart lives in its own copy of Rn or Rm. You know, these are not even the same dimension. So. I can. Mm, yeah. That's true. Yeah, I guess you can add a minor correction that like for every point M and its image f of m in here, there needs to be local chart like neighborhoods here and here, and then the restriction. Sure.
Arguing that if you pick the wrong alpha and betas, there are no such functions. But I think the definition is still fine because you're just saying for all local representatives, which restricts to only the alphas and betas where that composition makes sense. We're asking those two things.
Yeah, I mean, I don't see any problem. This is an object that exists for every beta and alpha, right?
So your confusion only shows up if you're talking about like smooth at a point, which is genetically finding smooth on the entire.
Yeah, I think this is actually fine. Right, this exists for any beta and alpha, for which some intersection is non-empty, but whatever, right? If it's empty, then don't talk about that map. All right. So we write C infinity of m comma n for all maps like that. We write C infinity of just m for R valued smooth functions with the standard smooth structure on R implied. And we have the category of smooth manifolds, where morphisms are all smooth maps. So for instance, you can check, it's a good exercise, you can check that all chart maps on, let's say, M, on any smooth map, a smooth manifold, all of its chart maps are smooth maps from M or from the neighborhood, corresponding neighborhood, into Rn with the standard structure. We never said that they are smooth, right? But they are actually smooth now with this definition. All right. So there's another philosophical note, which is that you can approach defining smooth structures from a totally different, like algebraic side. So this construction defines what smooth functions on a manifold are. And there's basically a statement that if you know what smooth functions on a manifold are, like locally on every neighborhood, what it means for a function to be smooth, then that's the same as knowing what the differentiable structure actually is. Because depending on what my smooth structure is, I will have a different set of functions that are smooth. And it turns out you can go in the opposite direction. You can define what smooth functions are and then induce the smooth structure from that. But anyway, turns out to be not super useful because algebraically the category of smooth manifolds is absolutely terrible, which is why algebraists only work with algebraic manifolds, because they actually have a nice dual algebraic category as opposed to smooth manifolds. Yeah. So manifolds geometry is dual to algebra, right? So the better you make your geometry, the worse your algebra gets. Right. The more restrictions you put on your geometry, the worse and more ugly the dual constructions in algebra get. So it's a trade-off. All right. So we can define also manifolds with boundaries. Basically, you just let's define R n plus as the set of vectors points in Rn such that xn is greater or equal to 0. So it's just the upper half space with the boundary included, and allow charts from some subsets of our manifold into R plus n, and for a map between some set you had in R plus n into R plus n is smooth. There's just a general definition from analysis. What it means for a map to be smooth on a closed set or a set with a boundary, it just means that you can actually extend it to a smooth map on an open neighborhood of that thing. If there exists open U tilde that contains U hat and C infinity extension, and a smooth extension of whatever this map is. So using this notion of smoothness, you can define what it means for transition functions between charts like that to be smooth, and that completes the definition of a manifold with a boundary. And then similarly, you can define corners, right? Instead of taking this to be the half space, take this to be like a lower dimensional, sorry, not lower dimensional, but yeah. But then there's like a whole hierarchy of corners, right? Of different dimensions. You can cut out like more and more coordinate planes out of, yeah. Anyway, we will need only boundaries at most. So the set DM is all points in M that map to this coordinate plane via boundary charts. What's that? Yeah, you can prove that this is actually independent of the choice of atlas. Notice that this has nothing to do with the topological definition of a boundary, because M is a topological space of itself, so it's already open in its own topology, just by definition. So it doesn't have any topological boundary. That's a point of confusion. It needs to be clarified. Is actually not a definition. So I wanted to give you an example of a map which is not smooth in this sense. So if you take square root of x, right, a map from R plus to R, this is not smooth on R plus because it cannot be extended to the left as a smooth function. Derivative turns to infinity. Okay. Okay. So now Diffeomorphism is a map from N to N. Actually, smooth map from N to N, such that there exists an inverse, which is also smooth from N to M. So literally isomorphisms in the category of smooth manifolds. And you can prove, number one, that Diffeomorphisms are homeomorphisms that are also open maps. So they preserve the topology in both directions. I mean, they're open just because the inverse is also homeo. That's pretty trivial. And then if these manifolds have boundaries and F is diffeo, then then the image of the boundary has to be the boundary, and the restriction to the interior is a diffeomorphism of the interiors. That's pretty easy. Okay, so let's go back to our examples of smooth structures and see whether they are actually diffeomorphic or not. So we had our example of M equals R, and I had this one atlas A tilde, which consisted of this x cubed, right, chart, and then the standard one, which is just the identity map, right? I claim that these two manifolds with these two different, as we found out, structures are actually diffeomorphic. right? So claim M with this structure is diffeomorphic to M with this structure. Can anyone tell me what the diffeomorphism is? Why? So let's try f of x equals x cubed, right? Then the local representative is first is identity circ f circ x to the 1 cubed, right? Which is identity, which is smooth, so that's good. And then the inverse, wait, no, that's it, right? Because this goes in the, f goes from, oh, this is confusing. I didn't say from which manifold to which this goes. So this goes from in this direction. No, in that direction. Right? So the local representative would be the map on M inverse, the chart map on M inverse, and then the chart map on N, which is identity. And F is x cubed itself. This is identity, which is smooth. Okay. So this is indeed a smooth map. And then its inverse, same exact exercise, is also identity and local representatives. So
Represented by identity.
I know. Who needs another go at this?
Maybe a diagram here would definitely have sense. Like, so if this is R with the x cube chart, this is R x. You have a chart here, which is again. So what you basically need to do is this psi beta that goes from here to here is nothing but x cubed. The inverse map is x to the 1/3. So what we need to do when we construct this representative from here to here is somehow cancel the non-smoothness of this 1/3, which is why you construct a map that goes from here to here as x cubed. So the composition of this one and this one is just the identity map, and going down here is just x, and you get a smooth map. And the inverse is just pretty much trivial.
So using this, you can actually prove that there's only one, that all smooth structures on R are diffeomorphic to each other, because you can just take, R is covered by some atlas, which consists of a bunch of smooth intervals that overlap, open intervals that overlap, and you have some charts which can be represented as functions with some plots, some smooth. That's right. Right. These are actually supposed to be invertible, stuff like that. And then you just shift them, add a constant to each of them, and glue them together into one global function, which you can then prove is actually smooth in that differentiable structure. And that will be the diffeomorphism between whatever your smooth structure was and the standard one. So there's only one smooth structure on R. Same for like a circle or any one-dimensional manifold. Now for two-dimensional and three, I don't know what the proof is. Okay. So examples. That's number one. Number two. So there have been discovered manifolds that have more than one non-diffeomorphic structure, right? the first example was S7, and it has 28 non-diffeomorphic smooth structures. These are called Milner's exotic spheres. Rn for any n has a unique up to diffeo C infinity structure, except for n equals 4, where no, there's many spheres, but 7 is just the first one that was discovered. Okay, so for n equals 4, our 4 has uncountably many non-diffeomorphic smooth structures, which is pretty terrible. So that explains why so many people are interested in low-dimensional topology, right? Especially four-dimensional topology. Probably just uncountable. I mean, continuum. Okay. And then in every dimension higher than 4, there exist compact topological manifolds that don't have any smooth structures. I already said that. Okay. So this is a construction that we will need for many purposes. First, recall that Rn has what's called bump functions. So bump function is a function. So basically, for any point in Rn and any two balls around it of two different radii. This is, let's call this B1 and this is B2. There exists a function eta Rn into R, which is smooth. So I'll just write it that way. Which is smooth, and eta is 0 outside of B2, and eta is 1 inside of B1. So it's 1 here, it's 0 here, and a smooth transition in between. You can construct them explicitly, but it should be pretty obvious that something like that exists. And basically, the only difficult part is transitioning from a constant to something smooth, which is not a constant. And that can be done, yeah, you know, something like e to the -1 over x always does that locally. So. Yeah. Yeah. Mm-hmm. Yeah, I can say C infinity to. Like that. Okay, so how can we use this? Well, if M is a smooth manifold, then we know that it can be covered by a locally finite collection of coordinate balls, right? So covered by locally finite collection of coordinate balls, U alpha, phi alpha. we can always pick an atlas that consists of coordinate balls and is locally finite. And then we can transplant these bump functions onto the manifold. So define f alpha as eta alpha circ phi alpha on u alpha, and then 0 on m minus u alpha. This eta alpha is the bump function. This is bump on u hat alpha, meaning it's 1 on u hat alpha and then 0 outside of some slightly bigger radius. And we then normalize these guys by writing, yeah.
One on all of u hat, isn't f alpha not smooth? Like, it's not even continuous.
We need to refine your cover a little bit and then get to.
Oh, this jump. Yeah.
It's like a bump function within u hat alpha, I guess.
You find that alpha, which is
So basically, u hat alpha would be like b2 in this case instead of b1.
No, that's not going to work. We need it to be 1 on that.
Do we know that cover coordinate balls has refinement?
What's that? I have my charts. I want this function to be 1 on this. Is that not true? Let me think. Maybe we don't need. So I want. Okay, let's look at this thing. I'm defining this object. This sum makes sense because it's locally finite, so only a finite number of these terms are not 0 for every x. And the point of this construction is that the sum of chi alphas at every x should be equal to 1, obviously. And is this going to work? Yeah, I think it's going to work if it's a bump in the sense that it's 0 outside of u hat alpha. So 0 on Rn minus u hat. Okay. So then everything is smooth. Should be fine. Okay. And these are C infinity on M. And of course, chi alpha on M minus U alpha is 0. Right. So here's the full list of properties of these functions that we've constructed. So number 1, chi alpha smooth on the whole manifold takes values in 0 to 1. Then the support of chi alpha is in u alpha, and the set of these chi alphas is locally finite in the sense that only finitely many of them are not 0 at any given point. And number 5, the sum of them is identically 1 on the whole manifold. So all of this defines a partition of unity, and we just proved that they exist on any manifold. and the reason for their existence is essentially paracompactness, right? Or second accountability. Well, no, paracompactness. Okay. All right. And we say that this partition of unity is subordinate to the cover by U alphas. So the support of every one of them is contained in one of the U alphas. And proposition, any open cover of a smooth manifold has a subordinate partition of unity. And that's just because we can always refine the cover to coordinate balls. And then this inclusion will be true. Okay. Here's a fun theorem that we can prove using this. It's called extension lemma. If I have a closed subset of my manifold, and I have any function that is smooth on A only, takes values in Rk. And remember that for it to be smooth on a closed subset means that it needs to have smooth extensions to like open neighborhoods of every point. Then for any open set, for any open neighborhood of A, any open set such that A is in U, there exists a smooth extension. So F tilde, which is smooth on U to Rk, such that F tilde restricted to A is the same as F. Okay. In particular, of course, U can be the whole manifold. So this is saying that any smooth function defined on a closed subset can be extended to the whole manifold smoothly. And I'm not really excited about going through the proof in detail, but the idea is that for every point of A, by definition of smoothness for this function, there exists a neighborhood. Like if I have my set A, for every point, there exists an open neighborhood to which F can be extended, including the ones at the boundary. And so we have, for every point, we have these F tilde P's, which are extensions to some small neighborhoods of the point P. And then we cover the whole set A by infinitely many neighborhoods like that for every point B, and infinitely many smooth extensions to every separate neighborhood. And they don't have to match in any sense, right? But you can make them match by multiplying them by a subordinate partition of unity and summing them up. That's basically the idea. So you take these F tilde P's and multiply them by a partition of unity and sum over all points of A. This sum is actually locally finite by definition of a partition of unity, which has to exist. And this will be our F tilde. And it's can be smoothly continued to the whole manifold by just setting it equal to 0 outside of the domains of these guys. No, of course not. And there's another notion which is useful, is so a smooth function on a manifold is called an exhaustion function if here's a picture. So I have, it's called an exhaustion function. If for every real number C, the pre-image F inverse of this ray from -infinity to C, including C, is relatively compact. So i.e. Its closure is compact. Okay, so basically the idea is to construct a smooth function whose pre-image for, let's say, every natural number, this is going to be the pre-image of from -infinity to 1, -infinity to 2, to 3, etc. And these guys are all compact or almost compact in the sense that the closure is compact. And then these compact sets slowly are supposed to cover the whole manifold, which they will, just because will cover the whole range of values. What's that? Yeah, so we're not going to quite do that, though. We're just going to prove that every manifold has an exhaustion function. So proposition. Every manifold has an exhaustion function. It's pretty easy. Let's just take V alpha to be a countable open cover by pre-compact sets. I studied before that it's possible to make them pre-compact, maybe sufficiently small. And chi alpha will be, because this is countable, this alpha can be taken to be just natural numbers from 1 to infinity. So this will be a subordinate POU. And let's define f of x as the sum all of these guys, right? So I claim that this is an exhaustion function. Oh, sorry, this is supposed to be chi n times n. All right. So f inverse of -infinity to c is going to be contained in the union I going from 1 to integer part of c plus 1 of these V alphas closure, which is a finite union of compact sets, which is compact. So this is contained in the compact set, which means it's pretty compact. So that's an exhaustion function. So this is helpful in a lot of proofs where you have some property that is easy to prove for compact sets, and then you can just extend it to any manifold by using an exhaustion function. Next small topic is Sartre's theorem, another named theorem that we're not going to prove. So, any questions about the construction so far? partitions of unity are mostly useful for integration of functions. In Rn, a set A has measure 0. If what? Does anyone know what it means for a set to be measure 0?
Covered by balls to make its total volume arbitrarily small.
Right. If it can be included into an open set of an arbitrarily small. If for any epsilon there exists U open such that A is in U and the volume of U is less than epsilon. Or can be covered by a set of balls such that the sum of the volumes of those balls is less than epsilon. Same thing. This is a bit more complicated because it assumes that we know how to define volumes of open sets. Anyway, okay. So a measure in general is not easy to define, right? There's a lot of arbitrariness in it, but measure 0 has a very natural, almost topological structure to it. You only need to define volumes of balls, but then it doesn't matter how you scale them locally. You can scale the definition of a volume over the whole space. The definition of measure 0 will not change because of that. Okay. So definition. On a manifold, I don't want to write this down, but on a manifold you can define a set of measure 0 by just using charts, right? So a subset of a manifold has measure 0 if only if all of its images under all of the charts that cover it are measure 0 in the corresponding Euclidean spaces, which you can check as a consistent definition. Doesn't depend on the charts. What's that? What? What? What is content 0? I guess I've never seen that notion. Okay. Okay. So here's a definition that's going to be super important over the next few lectures, whenever they happen, is the rank of a map. So let's say we have a smooth function between two manifolds. And let's say M has dimension M, N has dimension N. I'm going to use superscripts a couple of times for that. So this map has rank R at point P if oh, by the way, if this were a map between two Euclidean spaces, how would you define the rank of a map at a point? Mm-hmm. It's just the rank of the matrix of derivatives, right? Jacobi matrix. So we have to do something similar here, but we don't know how to differentiate functions yet, right? So we'll do it differently. For now, so this is written rank at P of F equals R. That's what we're defining. So if there exist local charts U, comma phi around P, and V, comma psi around f of p such that the local representative acting on a set of coordinates x1 through xm has the form x1 comma xn xm xm and then a bunch of zeros. Okay. So it has rank R if there exist coordinates on both M and N such that this map locally looks like just a basically an inclusion as a coordinate subspace, coordinate plane into the result. Okay. So the points where the rank differs from N or M are sort of special, which is why we have special names for them. So P and M is a critical point of F, if rank at P of F is less than N, the dimension of the target. No.
Why is it that in the equation you have
Oh, this is, wait, this is supposed to,
left hand and right hand have to be the same like from x1 to x and will be the same length.
it's supposed to be R. Yeah.
Is it that your x1 on the left hand side is the same x1 right hand side or the
Yeah, of course. I'm looking for special coordinates in which this function is literally this as a function from Rm to Rm. It's like I want this local representative to be exactly this function, right?
So
That's it.
basically,
Yeah.
you can take x1 to xm, split it up into x1 to xr and xr plus 1 to xm, and just draw
Yeah.
all the coordinates from r plus 1.
Yeah, so we can kill some of the directions, project them out, and then include it into some higher dimensional Rn as a coordinate plane. That's what happens. So the two special cases are maximal rank map, which we'll talk about more. But when the rank, so the rank can be at most the minimal dimension out of the M and N, right? R cannot be greater than the minimal between M and N, if you think about it for a sec, just based on the combinatorics here. Whenever it is less than one of them, that's a special thing. So this is called the critical point. Then f of p is called a critical value. Then otherwise, p is a regular point, and f of and a point q in N is regular value if all of its preimages all are regular. So if the rank is equal to the dimension of the target, then it's a regular point. If you think in terms of the Jacobi matrices, the Jacobi matrix has to be surjective for that to be true, for rank to be maximal equal to the dimension of the target. All right, so theorem. It's hard. For any smooth map, the set of critical values in N has measure 0 and N. Okay. Everything else, so almost everything is regular values. Almost everything in the image is regular values, right? And by the way, this theorem is completely local, right? It's pretty much independent of the fact that we are talking about manifolds, because the definition of measure zeros is local. So it's enough to prove this theorem for just Rm and Rn. So it's a theorem in analysis more than geometry, which is why I'm not really interested in showing you the proof. Okay, any questions? So rank is a very important thing to internalize because the next few lectures we're only going to be talking about that. Or some maps of some special ranks. Okay, and finally, I guess the last thing I'll do for today is restate familiar theorems to you. It's called inverse map theorem. I'm going to write it like that. And implicit map theorem. All right. Number one, inverse map theorem says the following. Let's say U and V are two subsets over N, open, and F is a smooth function from U to V. If the Jacobi matrix dFi by dxj at some point A is non-singular for some A in U, then there exist neighborhoods, one neighborhood of A, which is in U, and another neighborhood of the value f of A, V f of A, which is in V, such that F is a diffeomorphism when restricted, is a diffeomorphism between those two neighborhoods. UA. Diffeomorphism. Okay. So the moral of this is just that if the Jacobi matrix is invertible at a point, then the map is a local diffeomorphism at that point. i.e., it has an inverse, local inverse that is a diffeomorphism that is also smooth. And the second theorem, so obviously I'm not proving this because that should have been done in first year calculus. It's actually pretty difficult. Both of these are pretty difficult theorems to prove. You have to use like contraction principle and stuff like that to construct these inverses. What did you say? They're conceptually pretty difficult proofs. Like, you wouldn't instantly come up with, that proof. Pretty tricky. Anyway, so inverse mapping theorem is the following. Let's say U is an open subset of Rn cross Rk. And X comma Y is a point like that, Xn, and then Y1, Yk is a point in U. And let's say phi is a smooth map from U to Rk. Okay. It takes values. The arguments are in Rn cross Rk, and then it takes values in Rk. And phi of X comma Y equals C. Then if the matrix d phi I by dyj at xy ij goes from 1 to k is invertible, then there exist open neighborhoods, one for x, which is called Vx, in Rn, and one for y, which is called Wy, in Rk, and a map which is smooth between Vx and Wy, such that, I don't know why I'm doing this, because when we use these theorems, I'll never actually explicitly write out this stuff. Such that for any V comma W in Vx cross Wy, phi of VW equals C is equivalent to W equals F of V. All right. So this is the only meaningful line in the whole theorem. It just says that if we have an equation like this, and the derivative of phi with respect to the y's is non-singular, then we can locally solve for y as a function of x. And that's f. Okay. So W will be f of v, some function of v, and solves this equation. That's it. So next thing was to construct tangent spaces, which is what you were asking about, but that has to be next time. Any questions? Final? All right, thanks. I assume people are leaving already next week, right? Yes? Is anyone leaving next time? Next Friday? Or by next Friday? On Friday or when? What time? Do you want to meet on Friday? Okay.
My schedule's time translation variant.
Yeah.
We can do send out like one or something if everyone's out on Saturday.
All right. Last meeting was pretty small, actually, but it was, yeah.
The last meeting was probably because it had the location switched at the last time because they were doing.
Yeah, we changed the room. Some people were late, and whatever. Some people were not here.
Maybe it's because this time Alex shamed you in the email and says if you were skipping meetings, this is
Yeah. Next time is exciting. Tangent spaces, differentials, all that.
starting to deliver on promises of the
The first few pages of Walled.
Chapter 2, I guess.
Yeah. Okay.
No, real analysis is not so bad. The proofs can be annoying.